So let me write something in the channel. Let me see. Okay. So let me fix the sound. Okay, I can hear myself. So, sorry for the trouble. That we fixed the sound now, and let me start again. So it's a pleasure for us to have Carlos Salgado here. He's a professor in the Santiago de Compostela University, where he got his PhD in 1998, and then he moved as a postdoc to several places in Europe. First to Orsay for 3 years, and then to CERN from 2001 till 2005. First with the Marie Curie, which is a European fellowship, and then with the prestigious CERN fellowship in the theory division. He, after that, obtained the Ramón y Cajal to return to Spain, but he was awarded also second Marie Curie at Roma, La Sapienza, the main university in Rome, where he stayed from 2006 until 2007. And after that, he returned for good to Spain, to Santiago de Compostela, to the Instituto Gallego de Física y Altas Energías, or the Galician Institute for High Energy Physics. He soon became, after finishing the Ramón y Cajal, he got a permanent contract there as a contratado doctor, 2014 professor titular, and also as paid associate at CERN. He has been the vice rector of internationalization in the University of Santiago de Compostela since June 2014 until June 2015, and is presently the director of the Galician Institute of High Energy Physics since July 2016. That's almost 6 years. He's received, or he has actually won, the very prestigious European Research Council grants, first with a starting grant in 2011, and now since 2019 an advanced grant to carry these studies on basically quark-gluon plasma and matter under extreme conditions. These are the most prestigious research projects in Europe, and there are very few people in Spain who have these kind of projects. He is also the scientific director of the María de Maeztu Excellent Unit in the Galician Institute of High Energy Physics. He's part of the ALICE collaboration at CERN, one of the main experimental collaborations running now at LHC. He has more than 300 publications with more than 35,000 citations. Just considering only the theory, more than 200 papers and more than 12,000 citations. He's received several awards, in particular the Golden Medal of the Santiago Complutense University, as well as the Vidal Abascal Medal from the Royal Academy of Science in Galicia. At the moment, he has very good perspective of the future possibilities in high energy physics in Europe, in particular, because he's now the Spanish representative in the European Committee for Future Accelerators. And all this said, well, it's a real pleasure to have you here, Carlos, and I leave everything now for you. Let me remind the audience that they can make questions through the chat in YouTube. I'll gather all these questions and then I'll present them to the speaker at the end. Okay, thank you very much. So, Carlos.
Okay, thanks a lot. Can you hear me?
I can hear you perfectly well. I think the rest can do. Let me check with YouTube. If there is something wrong, I'll tell you.
Sure. So I can start. Thank you very much, Jose Ramon, for this kind presentation, which I surely not deserve. It's a pleasure for me to give this talk, this colloquium at Complutense at IPARCOS, and I only hope that we will meet in person soon. There has been a while since we met last time. So I tried the seminar to be accessible for everybody, and also especially for students if there are some students around. So the seminar is about how you form a quark-gluon plasma, and I'm going to explain what is a quark-gluon plasma in a few yoctoseconds. And well, maybe yoctosecond is, of course, one of the units of the International System of Units, but and this is the smallest unit of time for which we have a name, in fact. Just to give you an idea, light takes 3 yoctoseconds to traverse a proton. So 3 yoctoseconds is equivalent to 1 femtometer, 1 Fermi. Okay, so let me give you a general motivation for this type of studies. If you think a little bit on what normal high energy physics does, well, in fact, most of the physics follows this path. You try to look for the, well, you try to study the highest possible degree of simplicity in order to understand the fundamental building blocks of matter, and in particular, in this case, the Standard Model. So, and this is something that this principle of this reductionistic principle has led physics in particular to the success we know. Also, a very successful approach is to go a step up, if you want, in the degree of complexity of the systems, and ask yourself how the complexity of a system emerge from these fundamental interactions, from these fundamental theories we know. Because all the systems we know, most of the systems we know are complex in this sense, so they involve many particles. And this is the goal of the studies I'm going to talk about. This is something which is studied in many fields in physics, particularly in condensed matter physics, and also in other fields in biology, etc., etc. But the interesting thing for this quark-gluon plasma, which is a nickname for the type of studies I'm going to present, the unique thing is that you are dealing with a fundamental interaction, and you can study how this complexity is built at the most fundamental level, and you can add elements to this complexity starting from so the goal is to start from the highest possible degree of simplicity that we know already and add more complexity in the system. And this is the fundamental question we are facing. QCD, quantum chromodynamics, so the theory of the strong interaction, is perfect for this purpose because it has a very rich dynamical content with emerging dynamics that happens at scales that are easy to reach in collider experiments, and this is very important. And this, at present, well, at least in my opinion, this is the best available tool that we have to study the first levels of complexity. And going into something more concrete, what we are dealing with is equilibrium and non-equilibrium dynamics. Okay, I have a small movie here. I hope you can see it. So QCD, so Wilczek defined QCD as the most perfect physical theory. Possibly, if you get the Nobel Prize, then you have some preference for this theory, because an apparently simple Lagrangian, which is very similar to QED, has a plethora of emerging phenomena. For example, confinement, chiral symmetry breaking, etc. And what I'm going to talk about is the systems of phases of matter, like this quark-gluon plasma, in which the quarks and gluons, which are the fundamental degrees of freedom of the theory, are free and not confined inside the hadrons, as it happens in normal matter. In order to do so, we do experiments of heavy ion collisions at colliders, in particular at the LHC. And what you are seeing now is just an animation of a proton-proton collision. So this is a very simple animation, which in fact goes down before the starting of the LHC. Now, What happens if we put now a lot of matter in this collision? What we are expecting is that we create the conditions for for the production of this quark-gluon plasma, this new state of matter in which quarks and gluons are free in a macroscopic scale, and macroscopic, of course, in terms of QCD scale. So for us, a nucleus is a macroscopic state. Okay. So this is what happens in a real collision. So this is a snapshot of a real collision, an event display of one collision. You can read there. It was recorded in 2010 in the first round of the LHC. And you can see that each of these, well, you can see that there is a lot of tracks, a lot of particles there. And these particles, if you go backwards in time, were in a region of the space-time, very small, of the order of a nucleus. And in this region, the density is so large that normal matter don't exist. And what you have is this quark-gluon plasma. Okay, so we use nuclei because we need large objects, large in QCD scales. And so we have this macroscopic new state of matter. Okay, if you talk about the states of matter, of course, you are talking about the phase diagram. And this is what we know for the moment about the QCD phase diagram. You can see in here in this diagram, in the horizontal axis, it is the net baryon density. This is basically, if you want, the number of baryons minus the number of anti-baryons you have in your system, because the baryon number is a conserved quantity in QCD. And in the vertical axis, there is temperature. You see that there are basically, well, two phases there. There are more than two phases, in fact, but you can clearly see this quark-gluon plasma in this orange, and then the white, in which you have normal hadrons, protons, neutrons, pions, etc. Nuclei are down there in the at zero temperature, basically. And if you collide the nuclei, two different nuclei at different energies, you will create matter with different temperatures, and eventually temperatures large enough to go into these other phases. If you go to the right in the horizontal axis at zero temperature, very low temperature, you will reach neutron stars. Neutron stars, we don't exactly know whether they have a quark-gluon plasma inside, somehow a very cold quark-gluon plasma, or not, and this is something I'm going to mention now. The experiments we are doing in the LHC or RIC goes basically in this region of very small net baryon density, but very large temperature. So the experimental tools are listed there. We have the LHC, which is also colliding heavy ions 1 month per year, basically, typically. And it has collided, well, proton-proton, of course, but also proton-lead, lead-lead, and xenon-xenon. And other lighter ions are under study. And RIC, the relativistic heavy ion collider at Brookhaven, that has collided a lot of different combinations of different nuclei, small and large. For these medium energy facilities, like a RIC beam energy scan, so this is the same collider, but with different energies, or the FAIR at GSI and Nika Abdutna, if this is built nowadays, we don't know. Then you will be studying this region in which the net baryon density is not small, it can be large, and the temperature is not that large as in the other experiments, but it is still large enough, hopefully, to reach this the confinement transition. And then you also have cosmological observations for the neutron stars. And maybe in the future, we will access also this QCD transition of the early universe. Well, I didn't mention the early universe, of course. You are in the vertical axis at basically zero net baryon density. In in the early universe, you have the QCD phase transition, and maybe this is accessible with, for example, gravitational waves. Okay, so I have a, well, these are the tools that I was talking about. And I have a couple of slides about neutron stars. This is not the topic of my lecture today, but just to mention that this is entering a new era with gravitational waves and multi-messenger astronomy. And in particular, this is a nice work that is already 3-4 years old, in which Alexei Vorinin and collaborators have studied the cosmological observations, and in particular also this gravitational wave merger of two neutron stars, to put some boundaries in the equation of state of QCD. So this is really, really nice. So this is the state. So if you want, this is what you know from theory about the equation of state of cold nuclear matter. So this nuclear, remember, neutron stars are cold nuclear matter. So this is what you basically know, because you can compute with different techniques. The neutron stars, in fact, will need to know this region in the middle, and by using some fitting procedure, they could identify, they could put some constraints in the equation of state of QCD with this neutron star merger observation. So this is really very nice. It only indicates that this is a new era in QCD analysis of dense media. What they claim in these papers is that the existence of the quark matter core is very much favored in this analysis of the equation of state, and of course this in the future. So in other words, this neutron stars that have merged had a quark matter core inside. Okay. Okay, let me come back now to the topic of my talk, which is heavy ion collisions, and this is a simulation of the evolution of temperature with time in one of these nucleus-nucleus collision, and this is in particular gold-gold collisions at RHIC, at the Relativistic Heavy Ion Collider, with a square root of S 200 GeV per participant nucleon. Okay, so each a gold nuclei is almost 200 in total proton and neutrons. So you have to multiply, and this is the total energy. But we normally talk about the energy per participant because this is the most interesting quantity for us. Okay, so this is a simulation, and this is what we want to study somehow. Okay, so these are some questions accessible in heavy ion collisions. What is the structure of the colliding objects? So before the collision, if you want, because nuclei are different from nucleus, especially in the small x region of the nuclear wave function. And this fixes the initial conditions for the evolution, okay? The out of equilibrium initial stages. Then you have something in between, which is when this out of equilibrium system thermalizes, reaches some local thermal equilibration with some classical and also quantum effects, which are under study. And one of the questions is when or why or how hydrodynamics will apply, and I will comment on this. These two first stages, if you want, are the first order 5 yoctoseconds, or a little bit more, 1 Fermi over C. And this is the region which we know the least, and this is this interesting region in which you have we hope to study how collectivity, how complexity is built. And then after the collision, when this is equilibrated, you have the quark-gluon plasma, and you need to identify, you need to calibrate to study the properties of this medium. And for that, you cannot see directly, of course, because it disappears very quickly. You have to identify signals that characterize the medium with well-controlled observables. because at the end, what you want to understand is what are the building blocks, how they organize, etc., etc. Okay. So let me. The talk is basically organized in this time frame. So I will be talking first about the first. What happens before and exactly at the tau equals 0, the time of the collision, then hydrodynamics, and then the later stages. Okay. So for the initial stages, we need to understand what are the partonic densities, what are the structure of these nuclei, what is the structure of these nuclei in terms of quarks and gluons, and also how we produce the density of this matter during the collision, or if you want, how we produce multiple particles out of these nucleus-nucleus collisions. Okay, in here we can identify two regimes for those processes with large virtualities. So, for example, if you want to produce a Higgs particle, then this process is point-like because the virtuality is very large and the scale is very large. So the space-time, so it is very well localized in space and time. And this is normal perturbative QCD, and this is what we call the dilute regime. When we look at the smaller scales, so at larger, if you want larger distances, the partons are packed densely, so that there is a large density of these partons with smaller scales, and this is the dense regime. And this dense regime is the one that determines the production of the dense system. Okay, so I'm going to explain this in the next slides. Well, first, I don't know if this is a bit technical or not, but this is for those of you that know about perturbative QCD. You know that one of the, well, this is basically textbook material. You know that if you want to compute in perturbative QCD the production of a jet or the production of a Higgs particle, then you convolute the parton distribution functions, which basically tell you what is the density of quarks and gluons inside the nucleus or the proton at a given fraction of momentum x. You convolute these PDFs with the elementary cross-section, etc., etc. Okay, so these PDFs are extracted, so these are non-perturbative objects, and they are extracted from experimental data with using the DGLAP evolution equations, which are the best-known equations, perturbative equations for parton distributions. Okay, so we do the same for the nuclei, and if you compare the parton distribution, so for example, if you compare, this is for gluons, if you compare the density of gluons inside, for a proton inside a nucleus with the density of gluons in a free proton, this is what you obtain, okay? So this will be the ratio. As you see, if you go to very small fraction of momentum, you have much less gluons for those protons that are inside the nucleus than for free protons. If you go to larger fraction of momentum, then there is this, and this is called shadowing. If you go to larger fraction of momentum, you have a small enhancement. It is called anti-shadowing. Again, if you go up in fraction of momentum, you have another depletion called the EMC effect, and then something which is called Fermi motion. Okay, so this is a tool we need. This is something we need to do perturbative calculations, and at the end I will explain some of these perturbative tools that we are using. And one of the questions is whether these PDFs are universal or not, whether this whole process is well-defined or not. And what we have proven is that, in fact, it is possible to have these nuclear PDFs. Now, let me go, so this is the normal dilute regime. Let me now go to the dense regime. Okay, so I cannot use the pointer, unfortunately, but okay, doesn't matter. So the number of gluons that you have in a proton, for example, so if you look at the upper left corner of the slide, the number of gluons decreases a lot when you go to a small fraction of momentum. This tells you that this small fraction of momentum, if you want, are slow gluons. Okay, so those gluons that are produced in a, quantum due to quantum effects. So in a proton, there exists gluons with all momenta, and those that are slower are this region is very populated. There are a lot of them. Okay, now if you just think about a gluon as something which has some extension, and the extension is given by the typical size, and the typical size is given by the scale, and the scale is this virtuality q squared, then you can see that you cannot pack infinite gluons in a proton or a nuclei if they are growing as much as they are growing there. So at some point, and the place in which this saturation happens, when you cannot pack more, is very simple. It's very easy to estimate. The number of gluons is A times, so A is the number of protons and neutrons, times the number of gluons you have in a proton, which goes like 1 over x to some power. Then the typical size is 1 over pi q squared, the typical size of one of these disks. And then the available surface of a nucleus is pi a to 2/3, because the radius of the nucleus goes like a to 1/3. This automatically gives you that the typical saturation scale, the scale at which you cannot pack more gluons without them touching each other, so they are not independent anymore, is given by a to 1/3, so grows with a to 1/3, and also grows when you go to small values of x. So you can also understand this, that saying that you cannot put more color in your system because the color will reconnect, forming particles with higher color, and then at some point you reach. So you add these colors. Color is a vector scale. Is a vector charge. So you add these vectors, and they basically randomize. Okay. So the number of particles you produce then will be proportional to the number of particles. So this is very naive. It will be proportional to the number of gluons you have at this scale. And then you can do a very simple estimate with the number of created particles should grow as QS squared, because this is the number of particles you have in a nucleus, multiplied by the available surface, okay? And the available surface we can control with something we call centrality, with more peripheral collisions, those collisions in which only the periphery of the nuclei touch each other. You have less surface. With more central collisions, you have more surface. And this, in fact, provides a very good description of the experimental data. So this is some of this is almost one. So the first day experimental data you can take is the number of particles as a number of participants, which is the number of protons and neutrons that take part in the collision. Okay, these simple estimates can be formalized, and in fact they are formalized in what is called the color glass condensate. As we have large occupation numbers, we can just compute classical fields with the color-Yang-Mills equations, and the quantum corrections give you evolution equations. So this is a very well-developed procedure, which gives you the needed mathematics to this simple idea I have just put with colors. Okay, now we have produced some initial state, and this initial state is out of equilibrium. Okay, so you can see in there, time goes from left to right. So you have some nuclei before the collision. You can compute then the fields with the color-Yang-Mills equations I have just put, and this gives you the typical configuration is similar to the all color strings that we were studying like many years ago. So like extended color configurations in the longitudinal direction. This is out of equilibrium, as I said. Then you start to have some interaction of the gluons that have been produced, and at some point they thermalize. Okay, the evolution of this boosting invariant system can be studied in kinetic equations. This is studied, and this leads to something which is called the bottom of thermalization. The idea is, I'm not going to explain all the details, but the idea is very simple. At the beginning, you have a lot of the particles have momentum which are perpendicular to the longitudinal axis. Then these particles radiate. This creates some soft bath in which then the particles lose some energy by extra radiation. And then at the end, this radiative and collisional processes thermalizes the system in about 1.5 Fermi. Okay, so let me now go. So let us now assume that we have a thermalized system. If you have a thermalized system, you can use the laws of hydrodynamics. So hydrodynamics is basically an effective theory in which you have ignored all these elementary processes, this microscopic description, and basically what you have is the energy momentum conservation with some coefficients in which all the microscopic dynamics will be hidden. Okay, so these are the hydrodynamic equations, but for the relativistic case. So we normally study this for the non-relativistic case. And in order and this T mu nu, the energy momentum tensor, is given by the flow, the velocity fields, the energy momentum density field, the pressure field, plus some viscosity corrections. In order to solve these equations, you need also equation of state, the initial conditions, and to know where you stop, some freeze-out temperature. So this is basically the same as what you study in normal fluid dynamics, only that now it is written in terms of Lorentz invariant quantities. Okay, so one of the goals here is then to use these models to reproduce experimental data and to learn something about, for example, viscosity. This is something I'm going to explain now. The first thing you need is the equation of state. This is quite well known from theoretical calculations in lattice QCD and also in perturbative QCD. This is just one of the latest determination of the equation of state. Okay. So in which you can see that for example, the pressure when you go for large temperatures at some point reaches the Stefan-Boltzmann limit, etc., etc. So it will be an ideal gas. In the intermediate region of temperature, there is no ideal gas, and so from theoretical calculations, it is not very clear what it is. But from this experimental data, the study of experimental data, we will see that we can learn something very interesting. Okay, so let me explain what is one of the golden measurement in these hydrodynamical simulations. So if you remember the Euler equations from, at the basis of the hydrodynamics we study, the fluid dynamics we study in physics, then the acceleration of a fluid element is given by the gradient of the pressure, and if the energy density is proportional to the pressure in an ideal case, then a gradient of the pressure gives you a gradient of the energy density. So trivially, if you have gradients of the energy density, you will produce acceleration. Okay, now look at the plot there. This is a non-central heavy ion collision, and the matter is produced in this red or pink region in the middle. Now, it is trivial to see that the gradient in the horizontal axis is larger than the gradient in the vertical axis, the gradient of the energy density. So you have the same energy density at the center, and of course, it decreases much faster in one axis than in the other. So just by this simple geometrical consideration, you can see that you can prove that if there is this collective behavior, then hydrodynamics will produce more acceleration, so the particles produced in the horizontal axis will be faster, the momentum will be larger than the particles produced in the vertical axis. This is something just geometry, just anisotropies in the geometrical anisotropies translate into momentum anisotropies through the hydrodynamical equations. And for that, you need hydrodynamical equations. So if all these collisions will be independent, then there will be no correlation between the geometrical anisotropies and the momentum anisotropies. They will be completely independent. Okay, what you normally do to measure these anisotropies is to do a Fourier decomposition or in the azimuthal plane, so in the transverse plane of the collision, which is parameterized as you can see in there. And in particular, this V2, the first non-trivial, so the first Fourier coefficient is called elliptic flow. In this particular situation in which there is symmetry, so left-right symmetry, V3 will be 0, right? Because so the Fourier coefficient of cosinus 3 phi will be 0 just because of symmetry. Now, what happens, in fact, is that you have fluctuations and you have both V2 and V3 and also V4, etc., etc. So you have all the Fourier coefficients. These Fourier coefficients are studied, are extracted experimentally, and you have here data from Alice of the Fourier coefficients V2 and V3 as a function of the transverse momentum of these particles. And these Fourier coefficients are have been extracted from studying 2-particle correlations, 4-particle correlations, 6-particle correlations, and 8-particle correlations in the case of V2. This is just to be sure that you can see that whatever you do with more than 2-particle correlations, or with 4, 6, or 7, or 8, you get the same V2. And this is a clear indication that there is this collectivity. Now, with this experimental data and with other experimental data, plus the hydrodynamical equations, now you can compute quantities like the viscosity, for example. Remember, viscosity is one of the parameters we have in the hydrodynamical equations, which hides all the microscopic dynamics we don't know. And this is an extraction of this viscosity, which this was not the first one. It is only that it is one of the last ones, and this was in fact published in Nature Physics. This is the most perfect liquid ever observed. This is the smallest viscosity, and in fact, it has been argued that this is the smallest viscosity that you can have. And it is still compatible with quantum mechanics, with the uncertainty principle. And so the conclusion from here is that what we are creating in these experiments is the most perfect liquid ever. And that, of course, this was the state of the whole universe some microseconds after the Big Bang, because we know that the state of the whole universe was this quark-gluon plasma when the temperature was the same as the ones we are producing now. Okay, there is something funny or interesting, and the fact is that this hydrodynamics seems to work also in small systems. So we expected this to work in lead. I said that you need macroscopic objects, but this also works in proton lead, which is a much smaller system of the order of the proton of the radius, but also in proton-proton when you study those collisions with a lot of produced particles. So this is a puzzle still, because you don't expect proton-proton to thermalize even with this large number of particles. And this has opened. This is not a new story. This has almost 1 decade now, but this has opened a completely new way of looking at these collisions and to study the mathematical properties of the hydrodynamical equations. And in fact, what happens is that for large classes of problems, hydro equations have attractors, and so you have universal solutions independent of the initial conditions, and this is why this data can be also reproduced with hydrodynamics. Interestingly, if you look now, so people have looked also at HERA data, so electron-proton collisions, and this has not been found there. Okay, so in principle, there is no signs of collectivity in the much more fundamental, in the much more elementary lepton-proton collision. Okay, let me now change a little bit gears now, go to the final state and to look to other ways of studying the properties of this medium. And I'm going to talk about hard probes now. Hard probes, if you want to produce, if you want to study if you want to compute a process in which you have a very large scale, for example, if you want to produce a Higgs particle or a jet with very large momentum, transverse momentum, then this is the usual factorization approach that QCD tells us you can use, in which you separate the long distance dynamics from the short distance dynamics. The short distance dynamics will be the cross-section of quarks and gluons to produce something. And then the parton distribution functions I already mentioned. And then the other part, for example, so this partonic cross-section, if you take a quark or a gluon I and a quark or a gluon J, and you produce a quark or a gluon or another particle K, then this other particle may want to hadronize into, for example, a pion X, and this hadronization is given by also by long distance. Now, the trick here now is that so we have these large systems, a nuclei, and the large systems modify these long distance terms. It doesn't modify the short distance, it is the same, but it does modify the long distance. I already mentioned how you modify the parton distribution functions, but once you know how to modify the parton distribution functions, if you measure the modification of the hadronization, then you are measuring the properties of the medium, because the medium will modify the hadronization in a particular manner depending on its properties. And this is a list of observables that are used to study the properties of the medium. For example, one of the most popular one is this Quarkonian suppression. The intuitive picture is very simple. Quarkonia is the bound state of a heavy quark and a heavy anti-quark. For example, a charm, anti-charm is called well, it's a J psi, or excited states as the psi, etc. The upsilon is a bound state of a B bar quarks. And so intuitively, if you put this bound state in a system which is deconfined, then the potential between this quark anti-quark will be screened, and then they will be dissolved in the system. So the intuitive idea that was put forward in many years ago by Matsuai and Satz is that if you do this, if you measure J psi's or other quarkonia in heavy ion collisions, then you will see a suppression because you don't form these bound states because the potential is screened. Okay, and also interestingly, in this simple picture, you will also expect a sequential suppression because the excited states will belong to higher states, higher energy states in this potential, and then they will be dissolved more easily. So there is lots of data that led, in fact, to a much richer physics. in which we have now different effects. So this was the simple intuitive picture, and there is a lot of attention now. There is a lot of action in this Quarkonian suppression in the last, I would say, 5 years or so, which changed completely the way this is being computed. Because this screening, you can have several effects as a screening, rescattering, but also recombination. If you have a lot of quark antiquark pairs, if you have a lot of charm CC bar pairs, then at some point they can get together just by chance and recombine and form the J side. But also a transition between different Quarkonian states, because this is a quantum mechanical evolution, and then before the final state is created or measured, then there are also transitions. So Quarkonian nowadays is described as an open quantum system in which you have this quark antiquark pair in a system which is thermalized, for example. Okay, let me go now to the last part of the talk, which is jet quenching, and this is in fact my main area of research. Let me first describe what is a jet in normal proton-proton collision, or in perturbative QCD, if you want. So if you do a proton-proton collision or an electron-positron collision, so electron-positron is simpler, and then you do E plus E minus collisions, and then quark antiquark pair is produced. These quark antiquark pairs are produced out of equilibrium, off shell, and then they radiate gluons to become on shell. As this quark antiquark have a very large energy, the gluons that they radiate will go collinear with this quark and antiquark. And then at the end, the topology that you will observe experimentally is a bunch of particles that go into one direction, a bunch of particles that go into the opposite direction. This is the typical two-jet event in E plus E minus that we also study in particle physics, so introductory courses. Now, what happens if this quark that is radiating gluons and evolving in a medium and forming the jet, this evolution happens inside the medium. So this is what this jet quenching is about. So now let's put this jet, this parton shower, or we call this a parton shower, the proton, the quark that radiates a gluon that then splits into two gluons, etc., etc. What happens if this parton shower takes place in a medium? Okay, this is jet quenching. Several things happen here, and in particular, energy loss. And jets are extended objects with several different scales, and they are ideal to study space-time evolution of the medium. Also, if you follow a little bit what is going on now in particle physics and in the LHC, jet analysis, jet reconstruction is one of the main tools they are using now for basically everything, from measuring the properties of the Higgs particles to determining the parton distribution functions or searchers of exotica, etc., etc. So these are very fundamental tools nowadays in high energy physics. Okay, so this is again an event display. This will be this two-jet event that I was describing in electron-positron collisions, but now in a heavy ion collision. Okay, so I said at the beginning, you produce a lot of particles. You need to produce a lot of particles because you want to produce a very large energy density in the collision. But of course, this also obscures the identification of the jets. So you can see there in the left, this is the typical Lego plot. So one of the directions is the longitudinal direction, the other in the collision axis, the other direction is the azimuthal angle. You can see a cut in the transverse direction. So this will be the transverse plane perpendicular to the beam. And you can identify just by eye these two jets in here. And these two jets have very different energy. So this is the same event, but plotted in two different manners. It is very clear in the one to the right that so you have a jet of 205 GeV, and this is balanced with another jet of 70 GeV. So there is a lot of imbalance. And this is telling us that the second jet has probably lost a lot of energy when traveling through the medium. So this was originally a jet with much larger energy that traveling through the medium and radiating other particles, etc., has lost a lot of energy and appeared as a jet of 70 GeV. Okay, so this has been studied a lot at the LHC and also at RIC, first at RIC, in fact. And this is, well, this is suppression in one plot. This is, there is a lot of experimental data. So this is a small number of experimental data. But this plot is very useful to understand what happens. So what you do very often in heavy ion collisions is to do ratios of what you measure in lead-lead collisions over what you would measure in a normal proton-proton collision, and if you scale, if these collisions will be independent, if nothing happens. Okay, so if the ratio is 1, then nothing happens. What you have is just a superposition of normal proton-proton collisions. But if this ratio is different from 1, so something happens. So you can see in there measurements with color singlets, with photons or Ws or Zs. You see that the ratio is equal to 1, so nothing happens. You produce a photon, for example, inside this quark-gluon plasma. The photon basically do not interact with the particles, and you can observe this photon as you will observe in proton-proton. And the same with a W or a Z. However, if you now look to a pion, produce a very large PT, then this pion came from a quark or a gluon that has traveled through this matter and has lost some energy. So this energy loss means that there is a suppression, because the spectrum is very steeply falling. There is a suppression on the production of these particles. So particles which have color are suppressed, particles which don't have color are not suppressed. And this is basically this quark-gluon plasma. Sorry, this jet quenching, which allows you to measure the properties of the quark-gluon plasma. Okay, I have a couple of a little bit more technical slides, because there is something very interesting, and I hope it can be understood. So the physics is simple. Don't get afraid of the formulae. So in order to, so I said that a jet is a quark, quark or a gluon that radiates another quarks or gluons. So what you have is the propagation of these particles. It may be in vacuum, but also in the medium. Okay, so for the case of the vacuum, we know the propagators. This is the normal propagators we study in the course of quantum field theory. So you have the propagator for the quark, the propagator for the gluon, etc., etc. In the case of the medium, this propagator has non-perturbative contributions because it is traversing a medium with some collisions which are non-perturbative. But in the Eikonal limit, when the energy of this particle is very large, the formulation is very simple. In fact, when the energy is very large, basically the longitudinal direction is not affected. So you decouple the longitudinal from the transverse direction. And what happens is that you have a particle which basically goes, if you want, almost with the speed of light. And then it has some kicks, some Brownian motion in the transverse plane. This Brownian motion in the transverse plane can be described by the normal Feynman path integral, like the ones you use in quantum mechanics, only in 2-dimensional. Okay, so in 2 dimensions, in the transverse dimension, the dynamics is that of a normal Schrödinger equation given by here, in this case, in a path integral formulation, and in the longitudinal one, the dynamics is the couple. So basically, this is just time going this direction, and then dynamics in the transverse dynamics given by this kind of Brownian motion in the transverse plane. When the energy is even much larger, and then the potential in this path integral, the equivalent to the potential is a background field, or can be mimicked with a background field. which is classical, and we are neglecting here back reaction. We are neglecting any energy that the system could give to the medium. So there is the medium is there, and nothing happens to it. It's just a background, and then you have interactions with the medium. Okay, when you go to much larger energies, the kinetic term can be neglected, and what you have is this simple exponential, which is known as the Wilson line. Okay, and this Wilson line gives you the probability of no color rotation, so color survival. So what this Wilson line does is that, so it doesn't change the direction of propagation, it doesn't change anything. The only thing it changes is the color of this quark. Remember that in QCD, when you combine a quark and a gluon, then the color of this quark is different. Okay, so there, this quark is changing color when traveling through the medium, and if nothing happens, there is a color survival probability, which is given by this Wilson line. In technical terms, the Wilson line is basically the S matrix. Okay. Now, another little bit technical slide here. When you so you can compute this contribution. Imagine now that you have this C+ minus collision, which gives a virtual photon, and then the virtual photon goes into a quark-antiquark pair in the opposite direction. Okay, the radiation. So, and then you want to compute what is the radiation of one gluon in this configuration. You can do the same with a photon. It's exactly the same. Now, the radiation will be the radiation by one of the quarks plus the radiation of the antiquark, but these are quantum dynamical, so they are in the same, so they are quantum connected, and there are also interference terms, which in fact suppress the radiation in some regions of phase space. This is the first equation you see there is the radiation for a quark-antiquark pair in a given color configuration, and this is telling you that inside the so this is what comes out of the calculation. In fact, what happens is that the interference terms basically kill all the radiation outside the cone, which is determined by the quark and antiquark. So if you start with a photon, then there will be no radiation outside these cones, and this is what is normally understood as angular ordering. So the angles are ordered. Now, what happens? So I told you in the previous slide that the effect of the nucleus, well, so the effect of the quark-gluon plasma, or one of the effects, is to color rotate to induce color rotations in the quark and antiquark. So what will happen if we have this quark-antiquark pair inside a quark-gluon plasma radiating a gluon? Okay, before the radiation of the gluon, the quark will rotate. At some point, it could rotate independently on the antiquark, and then they will color decohere. So the effect of the medium, the effect of the quark-gluon plasma, is to make the quark and antiquark to be as a two different independent particles, so to break the color coherence between the two. And this is the result of a calculation in which you can see that when you compute now the gluon radiation out of this antenna, this is called an antenna, the interference terms are killed in the case in which the survival probability goes to 0. So they behave as independent from each other. Okay, this is the last, I think, the last technical slide. This very same effect is used to compute the gluon Bremsstrahlung, so the medium-induced gluon radiation. And this is needed because this is the main source of energy loss. So I said that you have the quarks and the gluons that travel through the medium. Each one of these can radiate extra gluons just because they are in the medium. So this is induced radiation. And this is the equivalent to Bremsstrahlung in the case of QED. So you have extra radiation and you have energy loss. This energy loss can be computed with this rate equation. This is basically telling you that there is some kernel, so some radiation, some emission kernel, and then this emission kernel makes the quark or the gluon to lose some energy. Okay, so there is a nice picture of this of the jet now inside the medium, which is depicted here, and this is very interesting because it provides a space-time picture of what is happening with the jets. So remember what I said, that if you have this quark-antiquark pair, and the quark-antiquark pair is inside a QCD medium, then at some point they lose color coherence and they become mass independent. So the radiation, remember the radiation, if they are not independent, is some part of the radiation is killed due to interference terms. If they are independent, this radiation is not killed, and then you will have some extra radiation. Okay, so at some point, this so you start with the quark-antiquark. It is in a color coherent state, and it behaves as being just one particle because it is color coherent. So the medium cannot resolve the quark and antiquark. At some point, they separate, and this is the first part in this diagram, this orange part. At some point, they separate and they lose color coherence. So you produce like two subjets, two parts in this parton shower, which are not connected to each other. So they will evolve independently from each other. And this is in contrast with what happens in the vacuum. On top of this, we will also have some medium-induced radiation, some this gluon-bremsstrahlung that I have just described. So each of these parts in the subparts in the jets will lose energy as one single object. Okay, so this provides an organizational principle for in-medium cascade, which is one of the things we need, and in particular also tells us something about the time evolution of the parton cascade. If we know the parton evolution of the cascade, we can measure the time evolution of the quark-gluon plasma in heavy ion collisions, which is the main goal of these studies I am describing. And I put just a couple of examples here, and this is basically the end of the talk. So this was the first example of a jet observable, which is devised specifically to measure the yoctosecond structure of the quark-gluon plasma. And okay, let me describe it a little bit. And it is also the first use of top production in heavy ion collisions. Okay, so the way you observe a top quark in high energy physics, in the LHC, for example, if you produce a top quark, it decays almost instantaneously to a W and a B, and then the W can decay into either a quark-antiquark pair in a singlet state or a lepton, charged lepton and a neutrino. Okay, so by now we have several time scales here. One is the decay time of the top. The other one is the decay time of the W. And the other one is the time in which this quark-antiquark pair will be still in a color singlet. Remember, it takes some time to break the color coherence and to break this color singlet. Okay, each of these times can be Lorentz boosted if we observe particles which are very fast at very large PT. So if we observe events in which the top is produced with large PT, then we will be seeing events in which all these times are longer. Okay, so that we can use them to study longer times in the evolution of the quark-gluon plasma. If we go to smaller PTs, then the times are smaller, and we can use them to study the smaller times in the quark-gluon plasma. Okay, and this is just, I mean, this is just one of the observables. If you measure the reconstructed mass of the W, reconstructed means that when you do an actual experimental analysis and you measure the quark-antiquark pair, maybe you don't reconstruct exactly the mass. But if you do this analysis and measure the reconstructed mass of the W with different boosts, so this is the transverse momentum of the top quark, then you can distinguish between different scenarios of the time evolution of the quark-gluon plasma. Okay, and the second one, and this is basically my last slide before the conclusions. This is a little bit different. So we realized a couple of years ago that if you study at the same time the suppression of high PT particles, the suppression of pions, if you want, at high PT, and we also study the V2. Remember, the V2 was the first the first harmonic in this Fourier decomposition and the azimuthal angle when I described the hydrodynamics. We have seen, this was kind of a surprise, that if you want to reproduce the two at the same time, then you have to kill the energy loss at the initial times in the evolution. So in particular, what we observed is that in order to reproduce the two, there should be no energy loss in the first 0.5 Fermis or so, which is of the order of 1 yoctosecond or 1.5 yoctosecond. This was very surprising. Nobody else before had pointed this out. And this opens the possibility to study these initial stages. Remember that what I said is that we want to, one of the goals that we have now is to understand how these complexities form. Okay, so this opens the door to study these initial stages where the complexities form using jet observables, which are very versatile because we have a lot of different jet observables. Okay, so this is a completely new tool to study the equilibration, and this is basically the goal of the project we have now with this advanced grant. Okay, let me go to the conclusions. So QCD provides a very powerful laboratory to understand how the first levels of complexity emerge from a fundamental theory, and in particular a non-abelian one. QCD has a rich dynamical content, and it is within the experimental reach. This is very important because if you have a very rich dynamical content, but you cannot measure it, then you cannot use it. Okay, so branches to other very active fields in physics, including cosmology or condensed matter, etc., etc. We can study now QCD equation of state with both cold and hot dense for both cold and hot dense matter with very different experimental tools, from heavy ions to neutron stars, and new data from the LHC and RIC, especially from the LHC. We have continuous progress on the characterization of the quark-gluon plasma, but there are completely new opportunities to study to directly access the time evolution of the system, and in particular the initial times, these first yoctoseconds in which collectivities form, and in particular with these jet observables. Okay, so this is the end of my talk. I was asked by the organizers to mention about the ERC grants because so this colloquia is also so the speakers, if I understand well, some of them or most of them are ERC grantees. I had 2 ERC grants for the moment. The first one was in the call in 2010 call. It was a starting grant. So starting and consolidator were not separated in this call. It was in a different, so they were separated internally for the evaluation. It was a consolidator stream, but okay. And this took place from 2012 to 2017, hot and dense QCD in the LHC era. hot LHC. And in the last couple of years, I have this other ERC grant, yoctosecond imaging of QCD collectivity using jet observables. And this is what I have been talking about in the last slides, a little bit more technical probably, yocto LHC. So I am free to discuss with you anything you will need about applications to ERC grants and how to best set the strategy to enhance the probabilities. Of course, the probabilities are low. This is very competitive, and small things may change successful proposal from an unsuccessful one. So, and I think I will stop here. Thank you very much.
Okay, thank you very much, Carlos. Thank you for a nice talk and a nice review of the situation about quark-gluon plasma. Probably the more, let's say, the part about the grants and how this management is carried out, we can leave it for later, and we stop the recording. But for this more scientific part of your talk, we have a few questions. Actually, quite a few. So I'm going to send them to you without private chat because they are in the YouTube that you're not seeing. And the first, I'm going to start with question. I'm going to start first with a question by a student, which is the following. There is Alexandre Salas, who is he's a PhD student, and he's I don't know if you can see the chat, my chat with you.
I don't. Let me try to.
No, if you are in, okay. Now there you can click on there should be a chat there. It looks like a.
Well, so maybe this is I can read it. Yes,
you can
maybe
read
this is a trivial question, but why, except proton-lead collisions, do we usually collide nuclei of the same kind? This is very good question, and in fact, we don't, and I haven't mentioned it. I am sorry, but so technically for a collider, it is difficult to collide asymmetric systems. For example, for the LHC, at some point they thought this was not possible, but then they did the proton-lead, and they proved this was possible. But many people thought this was not possible, and RIC, which is a collider which is built for heavy ions, do collide smaller against large nuclei. For example, they have down helium gold or things like that. And they do this type of collisions, for example, to study different geometries. I told you that when you have geometry, asymmetric geometries, then this translates into asymmetries in the momenta, and this gives hydrodynamics. So this has been done.
Okay,
the second one, I would like
the
to
second one is from a professor you know well, Felipe Llanes, who has several questions, and I'm going to give you a few of them, not all of them, because otherwise it's too long. So this is the first one. And it says, I would like to point out that the equation of state restrictions in neutron stars that you mentioned assume general relativity to hold inside the star, which is not well tested. They say the basically tests of general relativity are at zero density so far. For what can be said without assuming general relativity, see his work. I don't know if you have any comments about.
I'm not an expert on that. I understand that this is an ongoing discussion, and I prefer not to say something stupid, in fact.
Okay, fine. So he's made another question. Probably it's a little bit more related to the topic, which is this one. The viscosity plot is missing that of the hadron gas to the low temperature side of critical temperature. Since they calculate that here there would be.
Yes.
We would be interested to know if it has been instructed by Alice and if it has. What can you comment?
Yes. So I'm sorry, I have not mentioned many things, and in particular, I have not mentioned a lot of works done by people at your university. So forgive me that
I told you not to do so. So
forgive me that I've not been very kind. But I mean, I just gathered together some slides and put some extra slides with things I had, and this viscosity thing. I know much more the ones for the quark gluon plasma, and the extractions people are doing for heavy ion collisions. Yes, you are completely right that this plot is only for a part of the phase space, and in fact, this is the part of the phase space that was studied in this experimental data. Now, concerning whether Alice could measure this, I guess so, but I am not completely sure because these studies are still the type of studies they do are still quite simplistic in the treatment of the temperature dependence of the viscosity. So you have to go to lower temperatures. And people is normally interested in larger temperatures, and I wonder whether this will be better measured in lower energies, lower energy collisions at RIC, etc. Okay, so the
third question by Felipe.
How do Parton hadron fragmentation functions depend on the medium parameters such as temperature or quark density? Okay, so there are some modeling here. We as a community, not we or myself, but we as a community are working in providing this modeling more firm basis. And what is nowadays used is basically you do energy loss. Okay, so you could do something else because fragmentation function depends also on the virtuality. It follows the Diglap evolution equation, etc., etc. But what we do nowadays is basically energy loss. And for this energy loss, you have the rate equations I put in one of my slides. So basically, this is radiation, multiple radiation. It takes some energy, and this energy loss modifies the hadronization. It's for the moment is quite simple. There are some other observables which are more interesting that these fragmentation functions that are more evolved. Okay.
There is another one. Let me read it so that people know. This is Angel Nicola. He's still, apart from saying that it was an excellent talk, which I subscribe. Could you briefly comment on the present status regarding mapping the phase diagram?
Yes.
In particular,
Yes.
He means the programs such as the beam energy scan, especially regarding the QCD critical point.
Yes. So again, I'm not a very not very expert on this. I'm more on the high energy side, but so let me first explain. So what?
Maybe you can show the transparency.
Maybe I can share the slide. Let me try to do that. Can you see it?
Yeah, I can do. I can see it.
Okay. So the question is about this blob, this circle somehow in the middle, which is labeled as critical point question mark. Okay, so there is what lattice QCD tells us is that there is no phase transition from quark gluon plasma to normal matter at zero baryon density, net baryon density. Okay, so in the vertical axis there is no phase transition. And there are indications based on effective theories and other things that there is a phase transition, a first order phase transition at larger baryon densities. Okay, so if you have a region in which you don't have a phase transition and another region in which you have a first order phase transition, at some point there is a second order phase transition which is called a critical point. And there is an experimental program to look for this critical point and identify this critical point. in order to do that, you have to do collisions at lower energies because so if you go to high energies, then the net baryon density is 0 in the central rapidity. But if you go to larger to smaller energies, then the net baryon density is larger than, so it's larger, just because you deposit more baryons in the center. Okay, so there is an ongoing program which is called the beam energy scan at RIC. To my knowledge, there is no proof that so they have not reached this critical point. So there is no indication for the moment of this critical point. And there is an indication of the critical point in lattice data, but lattice is very difficult in this region of finite baryon density because, well, some technical thing with, I mean, some the net baryon density enters with an imaginary part, and then you don't have positive probabilities in the lattice. Okay, so this is difficult to reach theoretically, and also challenging to reach experimentally. But there is a whole program, and also FAIR will be looking for that. So this is what I can say for the moment.
Okay, so thank you very much, Carlos. I'm posting here in the chat just for you some discussion, an argument between two of the users in YouTube that you can read if you want, because I think it's we're probably over time with this, just if you're interested. I'll leave it for you.
So the first one is true. And in fact, there is occasionally there. Okay, let me try to say.
But you don't have to. I mean, I posted just for you if you don't want to.
Oh, okay.
No, because it probably is better if we just finish this so that you can see that there's been this discussion and you find it interesting, and maybe you can talk with these two users privately, right? Because there's been a long discussion. So thank you very much for your scientific talk. Everybody seems to be very happy in the YouTube chat that you're not seeing. So everybody's thanking you, and I extend this thanks once again for you. So in this last part, so we finish the scientific part and we move to the other more managerial stuff that we can do in Spanish. I mean, just students and all people who are not so much interested in this more in this part can leave, and we just probably will just stay here, the people in the Institute, to ask you about these things. Okay. So thank you very much, everybody who's been attending this talk. We appreciate very much Carlos being here. And now I'm going to move to the other part, which is not going to be recorded, if I understand correctly. Jesus. I changed to Spanish now. Jesus, I guess this is not being recorded anymore. Jesus, I've lost Jesus. Or José Víctor. No hace falta que lo grabéis ya, lo dejamos. Vale, muy bien.